All right, so today we're going to talk about relaxation and we'll get to demographics. This is the same thing that I said last time, except I spent the whole time talking about the homework because I have excellent planning skills. Um, yeah,
Did you read the note
which note?
on the board behind?
Ah, yeah. So there was a reading that was due last night, and I said I was going to move it, but I didn't do that. So thank you for doing the reading. I'm not going to talk about it till next time, because I'm not going to get to the star formation stuff today. So I'm going to run through the numerical homework, and then I'll talk about relaxation, and then I'll talk about the reading from the demographics. Reading. So now we're behind by 2 readings. So I'm not sure how I did that. I've been talking slower. I think. Okay. Let's run through the homework really fast. How did you guys find the homework? Pretty good. Um, uh, so the goal of this homework is to make you write a function. That's really it. Just to write a function and use it. How do you use functions? How do you write functions? So that's the primary purpose of this. So we had a couple of just try it out here, play around with these things using linspace. So linspace, if I want a number or array of numbers that goes from 0 to 1, np.linspace gives me the list of numbers between 0 and 1, and I have 10 of them in this plot. So you can print the fourth one with square brackets. That prints the fourth element. And then you can plot x versus x squared. And you should label your graphs always, because otherwise future you doesn't know what that graph is a graph of. Because even though you know what it is right now, in 2 weeks you're not going to remember. This is for when you're doing research. Label all your stuff. And I know this because I go through to plots that I made like a month ago, and I'm like, man, I wish I knew what this plot actually was, because it looks useful, but I don't know what I did because I didn't tell myself. And then here I had you write a function. So here we just defined a function square, and then we plotted it like that. I think everybody got that pretty well. The next bit was also, I think most people got pretty well. So everybody was comfortable using linspace to make an array of stuff. Whoops, I got to define everything. Actually, let me spend a minute with this first cell. So what's in this first cell? You should read it and get familiar with what's in it. But it contains kind of the basic stuff that we'll always need. So numpy. So we import numpy, which is the math package, and we call it np so that we save typing, because we don't have to type in numpy all the time, because we're going to type in np 500 times today. And then we'll import pyplot, which is our plotting routine, and we'll call that plt. You can call it whatever you want here. We'll call it plt because A, that's what everybody does, and B, it's short and easy. This line here, this matplotlib inline, that just makes the plots show up when you say go. So you need that line, otherwise the plots don't show up. Cool, a dictionary. The dictionary fairies must have brought that to me. Thank you for dictionary fairies. And then here's a bunch of numbers in CGS. The reason I put these here is so that you don't have to go look them up in CGS, and that way we're all using the same unit system. It's easier for me to grade if everybody uses the same units. So this batch of stuff, this header will be on every homework going forward. So it's the same numbers, the same packages. We'll use the same numbers in the same packages. Speed of light doesn't change over the course of this course, so that'll always be the same. There are actually measurements for whether or not the speed of light has changed over the history of the universe. Turns out no. Not enough to account for everything. So at some point in time, you may find yourself talking to a conspiracy theorist who hates the expansion of the universe, maybe. Anyway, gonna get totally distracted by that. So, so they a lot of times people will a lot of conspiracy theorists want the speed of light to be slowing down over time, rather than the universe expanding, which would work, but we checked and measured it, and it didn't. So the speed of light is constant. The universe is actually expanding. It's a bummer. Okay, so let's see. Other things that I wanted to mention. So when you do this problem, so we've got Lin space, which gives us 100 nanometers to 1,000 nanometers. So this is squarely covering the visible range. So we define a black body, and this just needs to take two arguments, the wavelength and a temperature. And if you had typed it all yourself, great. If you just used what I did at the bottom, that's also fine. So this is a bunch of math that I didn't want anybody to get bogged down on, which is why I just put it there. Because this is an exercise about writing a function. Oh, still, do what I want. This is an exercise in writing a function, not about the physics, though the physics is in there. So it needs to accept wave and temperature. And wave is going to be an array, but temperature is going to be a scalar. And this is something that I don't know, maybe you should say, maybe, I don't know how to set the homework up so that everybody gets it all right all the time. But that's not really the goal, is it? So one thing that a lot of people did, I'm going to leave that board there, because that's where I'm starting next time. One thing that you want to do, and several of you tried to do, and doesn't actually work, let's talk about it for a second, because I want it to work, and it slightly annoyingly doesn't. So you define this function, we'll call it BB, because I'm lazy, and it takes a wavelength and a temperature, and L we defined as some array, and then in our function we have something that goes like, let's just simplify it, e to the minus k, minus h c over lambda k t minus 1, and then there's some other numbers out there in the front. So our function looks like this. Now, we want to hand it a list of wavelengths so that we get our spectrum. We can't hand it a list for lambda and a list for t at the same time because it doesn't know what to do with that. So Python is nice in that it basically does what you want, and things basically behave like you want. So if I have a wavelength list L that I've defined with Lin space, for instance, this is an array so that I can square it. I can do L squared and it'll square every element in the array. I can multiply by 47 and it'll multiply 47 by every element in the array. So if I have one array and I do math on it, it'll just make that math happen to every element of the array. So if I just hand lambda into my black body function, then it'll just stick in my array here and do this to every element of the array. But if I stick in an array here and an array here, then I'm trying to multiply two arrays together, which is perfectly well defined if you tell it what to do. Telling it what to do in the right way is a little tricky. We don't need to do it. So in this, and I should probably stick a note in the assignment like this. T's got to be a scalar so that lambda can be an array. Otherwise, it doesn't know what to do. So a couple of you had some errors where I don't know, they gave you some weird errors. Let's look at what that error looks like and try to parse it for a second. So I got that and then that, and so this is what your result ought to have looked like. Oh, another glitch that people ran into pretty consistently is not calling the plot right. So let me talk about the plot for a second. So the plot, so plt.plot takes the independent variable first, and then the dependent variable second. So x is going to be, in my example here, the first element is going to be the list of frequencies that I'm plotting. And then the second thing that I handed is a list of valuables that is in the vertical axis. So so this should look like plt.plot L, and then B of L, and then a number, 3000. So the way I did it was with a loop. So I have this loop for T in 2000 through to 6000. L I defined up here, and then I call black body of L and T. L is this number, and T is my wavelength, and it plots out my black body. A couple of you had written the function right, but then called it not quite right, and that gives you some odd answers. So I didn't. It's hard to give feedback in that little comment box. So please go look at the solutions that'll be up. I forgot to post them. I'll post these later today, to see what you might have gotten wrong. So what it looks like if parsing Python errors is a little, there's an art to it. So if I just say black body of L, L is my list of wavelengths, and 3000 is my cool star, then that works. That gives me an array. I can plot that if I want. But if I try to give it a list of things, say 3000, say I have a list of temperatures, T equals 3000, 4000, and I hand this T, then it gives me this weird cryptic error. Operands could not be broadcast together with shapes 202. So how do I get my head around what this error is telling me? So when you're reading a Python error, you got to start at the bottom and read up. So you got to tell it what it stubbed its toe on. But Python doesn't tell you where you made the mistake. It tells you where it stopped being able to proceed. It's not always where the mistake was. So you got to look at what the code is doing at the time. And it gives you this call stack, which describes the state of the code. So let's look at that for a second. So the very first thing you should read is whatever's at the bottom. Could not broadcast together shapes this and this. So then you go back up and look and see, where did it fail? It failed on this line here. So here I'm handing it wave, which has a shape of 200, because that's how I made my thing, and temp, which is, so that's L, and temp, which is T, which has a shape of 2, and it can't multiply those two things together because it doesn't know what to do. If I had handed it something with the same size, then it would know what to do, but it wouldn't do what you want it to do, and that's not actually the right answer. So here it just gets stuck. So when you're trying to dig this out, it's best to read the call stack so you can see where you're having a problem. And then with this is why I gave you the code. Then you've got, if you have a problem, you've got to print every element, ask every element what it's doing and what size it is, and find the ones that are the wrong shape. Okay, does anybody have any other questions about this homework? Please take a look at the solutions, especially when the next homework comes up. Go mooch from the solutions that are up. Okay, that's it for homework. Let's talk about how relaxation happens. So we talk a lot about elliptical galaxies as big relaxed objects. And we want to talk about how they get relaxed. So we have this two-body, so we're going to say, okay, I've got n stars, where n is a large number. So I've got a bunch of stars. Each star is going to interact with every other star by gravitational dynamics, like this. How long does it take for a star to get turned by 90 degrees? So that means a whole change in its velocity. So we first try to sort out what the size, so we got particle 1 and particle 2, and they're coming at each other with an impact parameter of b. So that's particle 1's on a trajectory. It would make a straight line. The distance from that straight line to my other particle is the impact parameter, is the shortest distance, or close to the shortest distance that they're going to run into each other. So this distance b is we call it the impact parameter. It's how far, basically how close this is going to go, or how close it would go in a vacuum. So we want to know how much the perpendicular velocity changes. So we're going to assume that along the path velocity doesn't change. It's not accelerated. It's just redirected. No, that's a lie. It's accelerated. The velocity changes. It doesn't get any faster. So the total amount of acceleration in the perpendicular direction is just going to be the acceleration times the time interval. So delta V, and now here I am. So delta V perpendicular is going to be the acceleration times delta t. The acceleration is gm over b squared. It's further than that. B gets bigger, the force gets less. So we'll just assume that we're talking about the force where the force is biggest. So the acceleration is gm over b squared, and the time scale is, well, d equals r times t, so it's just the velocity times, so the time is just the distance it goes divided by the velocity. So that's like 2b, and maybe you want to call it 1b. That factor of 2, we're going to wave our hands at past later anyway. So the acceleration is gm over b squared, and the time scale is 2b over v. And this is delta v perpendicular. Everybody good with that so far? Yeah.
Where is A on the diagram?
A?
The acceleration.
Towards the particle. So the acceleration is going to be in this direction.
Okay, thank you.
Yeah. Okay, so now, so this is the change in v perp for one particle. So now we need to do is count them up. What we actually want, we can't average this. So what happens if I say, let's find average delta v perp? What's that going to be? If I've got, say I've got this test star, and I've got this guy, and then I got a whole bunch of other stars. So we're going to average over all the other stars that my test star could see, and we want to know what its net perpendicular velocity change is after interacting with all those stars. Given that we're going to assume that this is random, we're going to assume that things are randomly distributed. There's no boundaries. There's nothing weird going on. So if the stars are randomly distributed in space and you are traveling through a random distribution of stars and you're seeing kicks to the left and to the right, what is the average perpendicular displacement?
0.
Gonna be 0. Because I'm gonna have statistically just as many on the left and scatters to the left as I will to the right. So those will all wash out. So we need to sort out what delta v perp squared is. That's a thing that we need to add up. So this is a running thing that we'll go through a lot. You can't average a vector quantity because you almost always get 0. You can average the square of a vector quantity, and that makes more sense. So how are we going to do this average? So we're going to take delta v perp for one star, and then we'll add it up for a whole bunch of stars. So how many stars do we need to add it up for? Let's say I'm going on a path through my star cluster, and I'm going to see things out to a distance of b. So my star is traveling like this, and I'm going to think about everything that's a distance b away, and I'll have to worry about a number of stars that's equal to v times delta t. That's the total length that I'll travel. So so I just need to do an integral. Let's do it on this board. got all these stars in here, and I've got my test star here, and it's going this direction, and we want to average V perp squared over this cylinder. So that looks like an integral dV of V perp squared for 1 star, which I said over here is GM over VB equals integral d cubed V of GM over VB. Is that right?
Be squared,
Yeah.
right?
Oh yeah, do I square that? Did I square that? 2G, oh maybe there's a 2 in there. 2GM over VB squared? So what is dV? What is the volume element? So this is the thing that I'm integrating. What is dV and what are my extents? So my extent's going to go from 0 to V delta T, right? That's how long the cylinder is. And we go, R goes from 0 to B, and my volume element is dz dr pi r. 2 pi. Yeah. 2 pi r dr times 2 gm over vb squared. Now, okay, r is b, so let's say b, b, b. Now this b is going to cancel this b, and I'll do a little bit of algebra. So all I've done is said how long the thing is, and it's a circle, right? It's a cylinder, so I need that volume element, and we're squaring that, and then we're left with 2 pi. We got 2 gm over v squared, and then we're left with an integral and then we got a v delta t, and density of particles. I need to put in the density of particles. That's how many I'm going to run into in that unit volume. Integral from 0 to b of dB over b. So I'm just left with 1b. B is the radius for me. Just left with 1 because this is squared, but 1 cancels. And then all the rest of the things are just numbers that go outside. The only thing that I actually have to integrate is this d. So what is this integral? I've got the integral from 0 to b of 1 over b. That's actually a problematic integral. It's the log of 0. So okay, we got to call this b lower. We'll call this b pi. So this d1 over, the integral of 1 over b is just log b. So this is, so the average v perp squared is equal to v times delta t times n times 2 pi g m over v squared. That'll simplify in a second. Log of b low high over b low. So okay, so this is the total amount of deviation in square that I'm going to experience. So these all make sense. This logarithm, we have to wave our hands around, but it's a logarithm, so kind of doesn't matter a ton what I do with it, because I could be off by an order of magnitude, and what's the log of 10 is not a very big number. The log of 10 to the 6 is just 6. So it kind of doesn't matter what we put in here because it's logarithmic. But we'll say that the lower limit is where the deviation is maximal, and the upper limit is the size of the whole cluster. So we say that B min is where you get the velocity changes by the velocity, so a 90-degree reflection. If it's closer than that, it's going to do something weird. So we'll just say that that's the closest it gets is when it's going to hook by 90 degrees. Turns out it doesn't really get closer than that very often. So B min, I'm going to say is GM 2GM over V squared. So this is hooking by 90 degrees. Sorry, all the hand waving. I gotta remember how all the hand waving works. So actually, I want it back up there. So B min is going to be 2GM over V squared. So this is just saying 1/2 V squared equals 2GM over B is the potential energy. The potential energy is the change in the kinetic energy. So B max over B min is going to be the size of the box times what we just found, RV squared over 2GM. From the virial theorem, we're going to assume that we're going to invoke virial theorem, which is maybe a terrible assumption because we're trying to decide if the thing is relaxed in the first place. So invoking virial theorem before we've actually gotten to a relaxed object is kind of BS. But as I said before, we're waving our hands, so it's okay for now. So we'll just say that GM over R is V squared. So you can stick this V squared in here and we get that B max over B min is just the number of particles, because this is the mass of all the particles. This is the mass of one particle. So B max over B min is just like the number of particles. So this thing is just like the log of the number of particles that you're going to see. That's a lot of hand waving, but it works out okay. But everything else is totally fine. I don't need to apologize about really anything except for that thing in the log. So then we're left with the total amount of average delta V squared is then equal to 2 pi times 2g little m over V squared Vt and log of n. So this is the length of the cylinder, this is what's going on inside, and the radius of the cylinder, and that's just the log of the number that we got from waving our hands. Do a little bit of, so this is the result. So now we say, okay, what I'm looking for, this is how much mixing, this is how much redistribution of the energy that I get as a function of time. This is how far I go through the box. And what we want to say is that T relax is the time such that the average V perp squared equals V squared. And this implicitly defines the time by way of this equation. So I just say V squared equals 2 pi 2g m over V quantity squared V T relax times n times log big N. So we're defining T relax implicitly with this equation. So I got a V squared here and some V's over here, and we solve this to get here, I'll just leave this algebra up here because it's better to look up here than watch me do it. So we solve this guy, which is what I just have up there, for T, and we get that T relax is 1 over 2 pi NV V squared over 2gm times 1 over the log of the number. So what am I looking for? Is this useful? This isn't useful yet because I got velocities in there, and I don't want to have to know about the velocity of a thing. I just want to count the number of stars and ask if it's relaxed or not. So how do we get rid of velocity? Well, we use virial theorem because that works pretty good. So we just stick in virial theorem, and then this central thing V squared over G turns into the mass over the radius. Does that make sense? So this V squared and this G, V squared over G turns into mass over radius. That's the only thing that's changed in here. I've got the mass over the mass of the system over the mass of the particle. What is that? The total mass, I've got a collection of things that all have mass little m. They add up to a mass of big M. What is the ratio of big M to little m? What does that tell you? Do a math in your head. So I've got, I have little m particles. The total mass is big M. The number of particles times the mass of the particle gives me the total mass of the system. So the total mass over the particle mass gives you just the number of stars in the system. So this bit here just turns into the number of stars of the system in the system, and we're just left with the number of stars in the system times R divided by V over N. So R over V, this is the crossing time. So this is how long it takes to cross the object. So we do a bunch of algebra and wave our hands a bunch, and we're left with the relaxation time is equal to the size of the box over the typical velocity of the thing, of a star in the box, times the number of stars over the log of the number of stars, or the crossing time times the number of stars over the log. So this says that the time it takes, if what you're going to relax by is two-body processes, then the time it takes to relax is the time it takes for you to cross the box times the number of stars in the box. So you basically have to cross the box n times for every, or once for every star. Now this works great if you've got a small system, but when n is, let's see, do I actually have the numbers? No, I didn't. But if the size of the object is 200 kiloparsecs and you're going at 200 kilometers a second, the crossing time is 10 to the 8 years. And if you have 10 to the 12 particles, then I've got 10 to the 8 times 10 to the 12. That's too many years. Why is that too many years? Because that's much longer than the age of the universe. So we're clearly not relaxed by that method. So with a smaller object, if n is not 10 to the 12, but 10 to the 6, then I can have something that relaxes in 10 to the 6 years. That's pretty easy. Okay, does anybody have any questions about this? The thing that I really want you to make sure that you understand are the assumptions that get made, so this bit here, and that result, which is this bit here. Okay, I want to talk about violent relaxation because it's what actually happens. So let's start with the movie. So here I've got a collection of stars, and I didn't write down where I got this from, and I can't find it again, but I want to go reproduce this simulation. So I got this collection of stars, and they all see each other by gravity. There's nothing else in this universe. They all are going to get attracted to each other and then form something small and dense but has way too much kinetic energy, and a lot of it will escape, but some of it will remain and be a hard object. So if we think about what's going on, I've got I have a potential well, and that potential well is going to get deeper as time goes on, and things are going to fall into the potential well. Stars are going to fall into the potential well. If energy is conserved, that star will just exit the potential well again. So a star that starts over here will wind up over here with the same height, if energy is conserved. But it's not. for that guy. That guy's going to lose some energy to interactions with other cluster members or with other galaxy members. So it's going to wind up over here. But the guy that he gave his energy to is going to wind up over here and leave. So we have this reshuffling of energy where a bunch of things get a whole bunch of energy and get kicked out. But other stars, lose their energy to those things that got kicked out and hang around in the center. If I have 2 stars, I know exactly what that's going to do forever. Right? You'll do this in mech. If I have 2 stars orbiting each other, I know exactly what that solution looks like. If I have 3 stars orbiting each other, I have no idea, and this is a computationally intractable problem, which is kind of funny. I go from knowing exactly what's going on to having basically no idea. Now, that's not entirely true. If I have 2 stars, these guys are a binary, and then I have another star way over here, and he can't tell that there's a binary. This is a stable 3-body system. There are many stable 3-body systems. But if I have 3 things and they all have basically equal mass, or if one of them's littler, and they're kind of close to each other, and they all can see 3 bodies, what typically happens is one of the things gets ejected and the other 2 things get harder. So if I've got 3 bodies, one of them's going to get kicked out and the other 2 are going to get closer together. So they lose energy to the star that gets kicked out. So in this process, here we'll watch this now. So we've got all of these stars. Some of them get a huge kick from this process and leave, and some of them, and the rest of them, form this thing that looks like a galaxy. So this is it starts off uniform. Here's all our stars. And then they come in and they splash. A bunch of stuff gets kicked out and we're left with something that looks like an elliptical galaxy. It's kind of a cool process, and I'm going to write a paper that says that this process happens in small scale star formation, which I don't think anybody's ever noticed before. So how does this process work? Well, I'm going to go through some of this. And I'm going to go through something that Lyndon Bell put in his first paper because I think it's mathematically useful and physically very useful. And then, so this idea of violent relaxation was developed by Donald Lyndon Bell in 1967. And it's a really super good paper. Once you've taken statistical mechanics, you should go back and read this paper. But it's mostly a statistical mechanics result. I'm not going to talk about the phase space mixing, but I will talk about this cool linear result that he puts up right at the beginning of the paper, which says, so he does basically a dimensional analysis to say, well, okay, what happens if everything interacts with everything else at once? What kind of time scale should that take? So we'll do that. So we're going to take a detour and stop talking about astrophysics for a minute and just start talking about math, because I need it. So we'll do some violence in a second, but for now we got to do some non-violence, which is also a useful way to proceed. So you guys remember how a Taylor series works? Is that all too well? Fantastic. That's great. I remember when I first learned Taylor series, I was like, this is the dumbest thing possible. I have sine, and I now have a much more complicated way to write sine. That's kind of dumb. But then I realized that you don't need the whole Taylor series to still get most of the function. And that's why it's cool, because it takes something that's horrible and turns it into something that's linear. And if it's linear, I can solve it. Not like I think I might have a stab at solving it. I know how to solve it if it's linear. I know how to solve all linear equations, all of them. I know how to do that. It's well documented. And they can get very complicated, but the solution space, as long as it's, doesn't have any pathologies, as long as it's actually linear, I know how to solve that, and I'll show you. I'm going to start with some complicated function, f of x, and So I have some horrible equation, so f prime equals stuff. And I know, for instance, let's say my cartoon equation is f dot of x, and x is a function of t, equals, did I have a stupid equation? A simple cartoon example? Oh no, but bear with me 1 second. I forgot where I put those notes. The good notes are in my hydro notes, which if you go to the end by the so that you're looking at the vending machines. So when you can see the vending machines, turn around and it'll be on the right. It's in the corner. Yeah, no worries. Right. Squirrel brain is not gonna find the good notes. I have better notes out there that I wrote at one point in time. So anyway, so I'm gonna say that f of so I have some equation, f dot equals something horrible. Right, it's awful. Like, this is some horrible equation that I can barely even write down. But I know that I can take a Taylor series of Squiggle House. So as long as I can take a Taylor series, then I'm sorted. So how do I make this horrible thing work? So I've got f is some function that I don't know, but I know that I can Taylor expand it. So I can Taylor expand this around x naught. So x naught of t. No, x naught is not a function of t. X naught is position. X naught, I have an equilibrium. So I know f of x naught. I can then expand this around x naught plus delta x, right? So f of x is f of x naught plus what? F prime of x naught times delta x. So what's cool about this is that this is something horrible that I don't know. This is something that I do know, and it's just a number. This is something that I probably know, and it's just a number, and all of the actual variability is now in delta x, and so I took whatever is horrible, and now it's just linear in x, and I know how to solve that. So I'll show you in a second. The main stun of this is we want to turn my functions into something that's linear in t. So I'm gonna start with the example because I think that I'm gonna be a little less scattered if I have something concrete to work with. So we're gonna linearize the real equation. So 1/2 I double dot. That's how it starts. 2t plus v. So 1/2 of the moment of inertia, the second derivative of the moment of inertia, is twice the kinetic energy plus the potential energy. So I know that I equals some number lambda times the mass squared divided by mass times r squared. The gravitational binding energy is m squared over r times another very similar number. So the moment of inertia is lambda times the total mass times r squared. What's that? Oh, yeah. this is just a fudge number, so I can call it whatever I want. It's squared on the slides because it's handier later. The kinetic energy is 1/2 big M times, what do we call it, sigma squared? Did I call it anything squared? Average V squared. V equals minus GM squared over R. So I want to rewrite this a little bit. So E equals T plus V, right? So T equals E minus V. So 2T equals 2E minus V. So we're going to stick this in there. Minus 2V. Yeah, I got it backwards. And this becomes 2E plus V. Is that right? Yeah, 2E over M minus V. I'm going to divide through by the, so we're going to divide through by the M, and so we're going to be left with I double dot, so we got 1/2, I double dot, which is M R squared, double dot, equals 2E over M. Okay, E, conserved, constant. M, conserved, constant. Even though I did show you that we lose a lot of particles. So, for now, we'll do this constant. So now, okay, I'm changing the first term. Instead of being T, it's now E, and it's a constant, so that's cool. Minus V, which is now going to be plus GM squared over R. Oh, we divided by 3 by M. We divided by 3 by M. And that's the lambda squared. Okay. So I've got my 1/2 I double dot, which is lambda squared R squared, is E minus V. That's a constant, that's not. So now, I've got a differential equation. What does it look like? It looks like the second derivative of R squared equals a constant plus 1 over R. So this is R squared double dot equals A plus B over R. I don't know how to solve that equation. So let's make it look like an equation I do know how to solve. Now I have an equilibrium solution. So when you're doing a Taylor series or doing perturbation theory in general, you need to have an equilibrium solution. What's my equilibrium solution? My equilibrium solution is when that equals 0 and 2E equals minus V. Or I can say that my equilibrium solution is around R naught equals minus GM over GM squared over 2E, which I just get from this. So this equals GM squared over R. So we just solved this for R, and we're left with our equilibrium solution. So okay, now I've got an equation which is accurate and an equilibrium solution. We're going to do a Taylor series on R naught plus delta R. So, pause here for a second. I have an equation. This is f of R of t is my function. And it equals some stuff that I don't know how to solve, but I can linearize it and throw out all of the square things. So what I'm going to do, the first thing that I'm going to do, I'm going to plug in R naught plus delta R. Just plug it in. Second thing I'm going to do is do a Taylor series. Do a series expansion and an algebraic expansion. Then I'm going to throw out small things. How small? Anything that's got a square on it is going to be small. Then I'm left with a linear equation, which you always solve the same way. It's always an exponential, or sines and cosines, because you'll get a differential equation that permits exponentials and sines and cosines. So I'm going to leave this board up because I want all these things. I'll work on this one. Okay, so my equation that I don't know how to solve is 1/2 lambda squared r squared double dot, and I'm drawing them like Mickey Mouse ears to make sure that the double dot is outside of the square. The square is on the inside. Equals a number, 2e over m plus gm over r. So the first thing I'm going to do is plug in r equals r naught plus delta r. And the second thing I'm going to do is expand. So then I get 1/2 lambda squared r naught plus delta r squared double dot equals 2e over m, which is a constant, plus gm over r naught plus delta r. Just plug in. Straightforward. Sorry, that should just say plug in. Now we'll expand, and this one gets an algebraic expansion, and so we're 1/2 lambda squared r naught squared plus 2 r naught delta r plus delta r squared. We got the time derivative of that equals 2e over m plus, you guys remember the Taylor series of 1 over 1 plus x off the top of your head? That's it. So 1 over 1 plus x is 1 minus x. How do you see that? Well, I'm going to expand around x equals 0, so I plug in x equals 0 and I get my first term, which is 1. And then I take a derivative of this. The derivative of this gives me a minus sign because all this stuff is in the downstairs. So f of x is 1 over 1 plus x. F prime of x equals minus 1 over 1 plus x squared. Right? F prime at x naught equals minus 1. So when I assemble my Taylor series, I get f at x naught, which is 1, plus f prime at x naught, which is minus 1, times x, which is my x. So 1 minus x is the Taylor series of 1 over 1 plus x. I recommend just remembering that one because it's super useful. So let's Taylor series this thing. Oh, I don't have 1 over 1 plus the thing that I want. I got this r naught. So we've got to factor out an r naught from this. So I got gm over r naught times 1 over 1 plus delta r over r naught. There's a little bit of algebra to make this thing look like that thing. And then this looks like 2e over m plus gm over r naught. 1 minus delta r over r naught. So this equals 2e over m plus gm over r naught minus gm over r naught squared delta r equals, okay, this is the right hand side, So now I've taken this thing that goes like 1 over x, and now it just goes like x. 1 over x is hard to deal with in differential equations. X is really easy to deal with in differential equations. So that's the right-hand side. Now this thing is more easier to deal with. The left-hand side, this is also straightforward to deal with. I'm just going to throw out all the nonlinear terms. So we're going to say that delta r is like 10 to the minus 3. So delta r squared is 10 to the minus 6, and I can ignore it. Goodbye. And what about this term? This is the time derivative of r naught. What's it? 0. Why? Because it's just a number, which is a constant. So that goes away. So then the left-hand side becomes 1/2 lambda squared, 2, cancels this 2, r naught delta r double dot equals all this stuff on the other side. Or, oh, I started to see this stuff. Throw out small things, which we did. Step 4 is throw out the background. They're the equilibrium solution. And 5 is solve the linear equation. So now we got to throw out the background equation. The background equation is just this part and this part cancel each other out. That's what we got up here. We found the equilibrium solution by saying this was equal to 0. So 2e over m plus gm over r naught equals 0. That's it bit here. Ding. Now I'm left with delta r double dot equals minus, see what all do we have? We have g m over r naught cubed lambda squared delta r. So, what is r? Yeah.
I'm sorry, what did you just do?
Where? From here to here?
3 to 4, yeah.
I just rewrote this. So I got this over there and cleaned up this crap. So I just left with delta r, or r double dot, is equal to delta r times gm over r cubed now, and then my lambda squared.
Okay.
So I just algebra. This is a differential equation that everybody can solve in your head, right? So what is how? So delta r of t equals what? Is that? Yeah. This is sines and cosines. Sine of what? T. Omega t. What's omega? Square root of this stuff. Gm over, I'm going to call that rho, m over r cubed. And then there's another number in there that I don't care about. So omega is the square root of g rho times some lambda. But that's like 1. Square root of g of rho, do you remember what that is? That has a name. 1 over the square root of g rho is the free fall time. That's how long it takes for a thing to collapse. That's how long it takes for something to fall over. So we find that from this differential equation, so is everybody good with me going from here to here, or do you want me to talk about this being sine?
Yeah.
Okay. So this is an equation that, let's see, where am I wish there was one more forward. Do it over there.
Behind this one.
Yeah, this one slides, and this one slides. Oh, there's 2 over here.
Yeah.
One of them doesn't work.
He's having trouble getting it over
That went way further than I expected it to. I think this one. I love all these boards. It's not great for my ADD, but so okay, x double dot equals minus b times x. This is, let's do this different. Let's call this minus omega squared times x. This is a thing that is equal to its own second derivative with a minus sign and a thing. That is one of two functions. It's either sine and cosine or an exponential. So I can write this as x of t equals cosine omega t plus sine omega t. And you need boundary conditions to sort out what a and b are. So the derivative of, let's see, so if I have f of x, f of t is sine of omega t, then f dot of t equals, sine gets a minus sign in the derivative, is minus omega sine of omega t, and then f double dot equals, what goes here?
It'd be positive, right?
What's that?
Positive cosine.
Yeah, cosine is positive, and then we take a derivative of this. The derivative of cosine is just sine, so we still get a minus sign. We get another omega, and we get sine of omega t.
So the
Sine
derivative of
cosine
the
would be
sine,
positive.
yeah. But then we do get the negative at the end. So
Yeah, so how do I remember which one gets a positive and which one gets a negative when I screw it up? So we're looking at 0, so the slope of sine is positive, but the slope of cosine is negative. So cosine picks up the minus sign. You got to draw the right picture, and don't trust that your hand is going to do it right for you. You're going to get it wrong before. So they pick up a minus sign. If I have f of t equals e to the I omega t, then f dot of t equals I omega e to the I omega t, and f double dot of t equals minus omega squared e to the I omega t. And my favorite equation, e to the I omega t, is cosine and sine. E to the I theta is cosine theta plus I sine theta. This is one of the coolest things in the universe because, yeah, I cannot actually understate how important this relationship is. This relationship makes quantum mechanics work. It makes your cell phone work. It makes waves on the ocean. It's so powerful. But this relationship, we relate e's and cosines. So if a thing is its own second derivative, then you know you're going to have either an exponential or a cosine, and if it's negative, then you need an imaginary number or you need a cosine. If it's positive, you get a real number here or an imaginary number there. Good. You'll be happy with this differential equation. The other one that you should know, just off the top of your head, x dot equals ax, x equals e to the a t. That's an exponential. Okay, so what do we do over here? Oh, you get sticky. So what do we do over here? We started with this equation. Uh-oh, fart. Anybody got a power cord?
Yes.
Thank you. Otherwise, I'm gonna die. Really, the only sad part is the video gets cut off. I'll keep talking. I'm not battery operated.
Sorry,
Oh, no worries.
Box.
No worries.
Found it.
Dope. Thank you very much. Pop. Ding. Okay. So we started with this equation that I don't know how to solve. But it's just the virial equation, but that's okay. We said we know one solution where this equals 0, so that's cool. We then expanded around our equilibrium solution. We just plug in, expand everybody, do a Taylor series and some algebra expansion. We throw out all the squares, and then we're left with something that we can solve. Now I know that you're going to be left with something that you can solve, because I know that I'm turning these into linear equations. So I know I'm going to get something that looks like this, and I know I'm going to be able to solve it with sines and cosines. Which is what the beauty in perturbation theory is. It takes these complicated equations and it turns it into sines and cosines. Okay, does anybody have any questions about that? What we're left with out of this is the frequency, or the period, for this thing to for all the stars to interact with all the other stars, kind of one big swoop. The period for that is 1 over free fall time. So this is the basics of violent relaxation. So yeah, so in violent relaxation, it's fast. All the particles communicate with all the other particles at the same time, interact with all the other particles at the same time. And the period is roughly the free fall time. The time scale is roughly the free fall time. And it's necessary for things to become equilibrium in astrophysics. It's the fastest way to relax things. Okay. That's all I'm going to say about relaxation, I think. Here, oh, let me put this up again. Here I do all the things that I did there, just in one shot. There's not a lot of talking, it's just the math, but it gets you through everything. It's all the stuff that I just did. So, I'm going to stop talking about relaxation and I'm going to talk about demographics. So first I'm going to run through the reading on the demographics. So the next section that I'm going to talk about are what do collections of galaxies look like? How are galaxies related to each other? What are the systematic trends that we can talk about galaxies? Okay. See, magnitude and mass I talked about, I think. This sentence threw people off. dN is defined as the mean diameter of an ellipse within which the average surface brightness corresponds to a value of 20 magnitudes per arc second squared. So this is kind of a funny definition because it's defining the radius not by an integral, but by the bound on an integral, which feels kind of backwards. So I is the total light. Let's see. Sorry. If I is the surface brightness, it's a function of R. Then the average brightness is the integral of I times 2 pi r dr from 0 to some radius, r. So this is the average surface brightness as a function of r. Where you go with that? Just made it a polar coordinate thing because everything's round. So when the average surface brightness is 20.75 magnitudes per arc second, this equals the integral from 0 to dn of I times 2 pi. So what this sentence is saying is dn is defined as the mean diameter of an ellipse within which the average surface brightness corresponds to a value of blah. So it's the radius of an ellipse. Yeah, I made it a circle because it's easier to write that way. It's the radius of an ellipse such that the average surface brightness is 20 magnitudes. Again, the reason that we define things, the reason that we define it is this way. So we're trying to define the radius of the ellipse, or of the elliptical galaxy. So an elliptical galaxy, you know, is a big fluffy thing, and if I look at the surface brightness as a function of radius, it falls off. There's noise in my detector, so I can't see perfectly black with my CCD. I see noise from the temperature, from all kinds of stuff, so there's noise. So out at some certain distance, I can't tell where the galaxy stops and where the noise starts. So I can't actually tell you what the radius of most of these galaxies are. But I can get a fair bit of saying, well, okay, let's think about some fraction of it. So we'll say we've got a certain total volume. Let's see how big that volume or that brightness is. This is something that's way above the noise floor, and the amount of light that's out past it is pretty small because the light falls off. So it doesn't really matter that I'm missing that light. We'll talk about DN again when we get to D signal. Okay, if we say that dark matter isn't made of baryons, is it made of particles that we know? I don't know. Probably not. So, almost certainly not. Why? So let's see. So what do we know about dark matter? We know that dark matter interacts by gravity. We know that it does not interact with the electromagnetic force. How do we know that? It's in the name. It's dark, so there's no light, so there's no electromagnetic radiation. Light is electricity, right? We know it doesn't form by the strong force. It doesn't interact with anything by the strong force. Otherwise, we would see it. It would interact with nuclei. The strong force is, by its definition, strong. So it would form particles. We don't know of anything that we don't have any particles in the standard model of particle physics that only interacts with gravity and not the other ones. So I'm not really sure. We know that it's not neutrinos. I'll tell you why later. It's probably not any of the particles we know. So probably not. For the ratio of baryons to dark matter, why are we neglecting everything that's not a baryon? Well, the other things that are not baryons are leptons, which are like electrons, and they weigh basically nothing. You know, electron mass is 0.1% of the proton mass. We can ignore all the free electrons. And anything else doesn't live very long. So nothing other than the proton lives very long. The neutrons evaporate. Mesons all are short-lived particles. So any two-quark thing is going to be short-lived. So nothing else really lives for very long. So we can really, without missing too much, just talk about the protons, or the protons and the neutrons. And that covers the whole energy budget of the universe. Are ellipticals just spirals that haven't fully recovered from a merger? That's an interesting question. No. So they become elliptical because the angular momenta add. So if I have two spiral galaxies and one has an angular momentum that's this way, so it's rotating this way. The other one has an angular momentum that's this way, so it's rotating that way. Let's do it this way. Actually, sorry, I got a left hand and a right hand. So this one is rotating this way, so its rotation is going the opposite direction of my thumb. This one is rotating this way, so its angular momentum is going the same direction of my thumb. They collide. Their angular momentums add, and the net angular momentum goes down, so you have something that's not going to make a disk anymore. So after you add all of these random angular momentum vectors anymore together, you don't have something that has one coherent angular momentum vector. So, so ellipticals come from smashing a bunch of stuff together randomly. Now you can smash a bunch of stuff together and still have something with net angular momentum. We'll talk about that a little later. Is the fundamental plane the same for all galaxies? I don't actually know. Probably not. Oh, how am I on time? Oh, probably time to be done. So the fundamental plane is probably not the same for all galaxies, but I don't know enough to know. I bet that there's a good body of literature on that about fundamental plane on various types of galaxies. That's an interesting question. Let's see. Do non-luminous galaxies exist? Yes. There are a lot of galaxies that aren't giving off very much light because they're little. Finding them is tricky. What is the tilt of the fundamental plane? I will get to that. I think all of those I'm just going to stop there and call it a day. Because all of these are interesting seeds for talking about demographics on Thursday. Any other questions? Anything anybody needs to talk about?
I have a question.
Okay.
Okay, so to my understanding,